called Detecting Corks with Irving, Dyer, and Nielsen.
Thanks a lot for the invitation. And let's just announce what I'm going to talk today. This is going to be joined with Irving and Ian, who are the two excellent speakers. Came before me today, so it's a hard task to follow. Okay, so I'm excited to share this result. So let me first begin by discussing what are quarks. So here's the definition. So a quark is a tuple of an integer homology sphere y, integer homology sphere y. By the way, is this readable? I mean, like, is there no glare on anything? There is a integer homology sphere y and a contractible four manifold C, such that boundary of C is y. Why we think of it so oriented? So boundary of C is y, and moreover, y is equipped with a diffeomorphism. So let me call it tau, such that tau does not extend over C smoothly. So the cartoonish picture looks like this. I have a contractible manifold C, I have the boundary y, and on y I have a diffeomorphism tau. This diffeomorphism does not extend over C. So such tuples are called quarks. Okay? So here's an example. So first example of this type was given by Abhishek. Okay, by the way, before I go to an example, maybe I should mention the curious / interesting property about quarks is that even though this diffeomorphism does not extend smoothly over C, it is known by work of Friedman, the work of Friedman, implies that tau does extend topologically over C. Okay. So there will be no C infinity extension of tau, but there will be a topological extension always. Okay. So it sort of goes to the dichotomy between smooth and topological category, and that's why, in some sense, this is interesting. We will go into like reasons why is quarks. Why are quarks interesting in a moment? So first example of quark was found by Akbarud in 1991, where he showed the following manifold, which is +1 surgery on, let me call it 946, could also be 946 meter, depending on your convention, equipped with a certain diffeomorphism and a contractible bound is a quark. Okay? So I can draw this knot 946 for you quickly. So here's the knot. This is the knot 946. So what I do is I do a +1 Dane surgery on this knot. So meaning I take away a regular neighborhood of this knot and I glue in another torus, but with a specific boundary diffeomorphism that's specified by this surgery coefficient. So this is a 3-manifold. So that's my 3-manifold here. Okay, that is a 3-manifold Y. I now need to specify the diffeomorphism of the 3-manifold. The diffeomorphism of the 3-manifold is given by the following. So you see this knot admits a symmetry. So you can think of an axis that is coming out of the boat and hitting you. So if you rotate 180 degrees with respect to the axis, you see you get the knot back. So that is the symmetry of this knot. That symmetry, it's an involution in fact. So if I rotate 180 degrees, you get the knot back. So that's an involution on the knot. It induces an involution on the surgered manifold. So on +1 surgery on 946, I have this style. So this is going to be the involution of the surgery. And then what is the contractible manifold? Well, it turns out that this knot 946 is a slice knot, meaning it bounds a smoothly embedded disk in B4, the kind of disk that, or like one type of disk that Irving was talking about earlier in the talk. So whenever you have a slice knot, then you can do +1 surgery on the disk, and you can show that it's actually simply connected. So it will bound a contractible manifold. So this contractible manifold here is the contractible manifold that you get by doing surgery on this slice disk. Just to keep in mind that whenever you have a slice knot, there is in some sense, a canonically assigned disk associated to, contractible manifold, so that its boundary is surgery on the knot. So that is the contractible manifold. All right, fine. So that is an example of a Cork. So, but like, to be honest, why should we care? Okay, why should we care about Corks at all? Okay. So this sort of goes back to a theorem of Kurtish, Friedman, Hishing, Strong, and independently by Mudgave in 96. So recall that we say two manifolds are exotic copies of each other if they are homeomorphic but not diffeomorphic. So what these people showed is that any two exotic smooth structures on a simply connected topological 4-manifold are related by a Cork twist. Okay? So let me explain what this operation Cork twist is, because we haven't really talked about it. So the point of Cork twist is this. So suppose I have a closed manifold X. So what this operation is that it first finds an embedding of a given Cork. So let's say this is my given Cork C with boundary Y inside X. Okay. And then it reglues the Cork by the boundary diffeomorphism. Okay. So I reglue C by tau. So that is where the twist word comes from. So if I reglue by the boundary twist, I perform an operation that is called a Cork twist. Okay. So a manifold, a 4-manifold, and its twisted version where I've like reglued the boundary by the twist are generally, there is no reason for them that you'd expect that they are diffeomorphic. They are homeomorphic, in fact. This is a consequence of Friedman's work. So you sort of expect that maybe, well, you're getting exotic copies of a given 4-manifold. And the theorem is that any two exotic smooth structures that you can write down on the 4-manifold must be related by this operation. There will be a Cork that you will find an embedding of that Cork, and if you reglue by the twist, you will get the other exotic smooth structure that you would. Okay, so this is about like two exotic structures. This theorem was improved quite a bit by Melvin and Schwartz in 2019, so quite a lot after the work came out, this work came out, where I'm not going to write the entire theorem again, but sort of the idea is that here we say take any two exotic smooth structures. Well, you can consider n many different exotic smooth structures, so n many different smooth structures on a single homeomorphic manifold. So all of them are homeomorphic to a single four manifold, but their different morphism classes are different. So the thing is that if you have any finitely many smooth structures, they must always be related by an order n Cork twist. So in this example, you see this is an order 2 twist. You can think of if this diffeomorphism here was, if this diffeomorphism here was order n, then you could have performed this operation n many times. So like you glue by 1 twist, you glue by 2 twist, you glue by 3 twist, and so on. Each at a time, maybe you're changing the smooth structure. And indeed, their theorem tells you that this kind of thing is also true for any finitely many exotic smooth structure by an Cork of higher order. Okay. So if I'm interested in studying exotic smooth structures, I could hence think about the following question, that is, what are all possible Corks plus what are all possible embeddings of Corks, and then I'll get a handle on exotic smooth structures on four manifolds. Okay. I can, by these powerful theorems, it tells you that it's in some sense a fundamental object that if you are interested in like smooth four manifold topology and the dichotomy with the topological side, maybe you should also be interested in Corks. So, also recently, a slight generalization of the definition of Cork that I had in here was proposed by Lynn, Luberman, and Saviliev, where what they define is called a strong Cork. So, what is a strong Cork? So strong Cork is a Cork such that, so is a Cork y c tau such that tau on y does not extend over any Z homology ball. So, just to appreciate the distinction between the previous definition of a regular Cork was my Cork twist is not supposed to extend over a given contractible manifold that will be specified to begin with. This definition is slightly stronger or weaker in whatever sense. So now it's saying that, well, I can pick any homology ball W for which boundary is y, and I'll put this condition that tau is not going to extend smoothly over that homology ball. Okay? So not really specifying a contractible manifold to begin with. So this sort of this sort of actually goes into this philosophy that maybe what is so special about Corks is that something with the three manifold and the diffeomorphism that you're picking on the boundary. Maybe the three manifold and the diffeomorphism you're picking on the boundary are so special that the diffeomorphism will never extend over any homology mode. Maybe it's an inherent property of the diffeomorphism and the three manifold itself, not really about the four manifold that it covers. What are some examples of strong Cork? Well, the authors in this paper, this was in, I think, 19, if I'm not wrong, and the authors also showed that, so the example is that they showed the absolute Cork is strong. Okay. Okay. So, I mean, maybe you buy, what I'm trying to tell you is that, maybe there's reasonable reason for you to be interested in Corks, then you should ask the question, how to detect Corks and what are the candidates. Okay, so how does one detect such an object? What sort of tools do you have in your hand that you can use to detect such an object? All right, so let's start with for example, the absolute Cork. So typically, one would consider an embedding of, let's say, a given Cork or a prospective Cork in a closed four manifold X, okay, and then show that Cork twist will change a particular type of smooth four manifold invariant. So, I mean, the reasonable tools that we have in hand, let's say Seiberton invariant or Oswald-Szabo invariant or Donaldson polynomial. So, we're going to use the four manifold invariant to show that when you have this twisted copy of your original manifold X, they have different values for one specific type of such invariant. So, if we look at the Akbalut Cork, the way Akbalut showed in 1991 that, why is this the Akbalut Cork, is that he embedded, so Akbalut embedded last one surgery on 946 inside once blown up K3 surface, and then showed that if you reglue this Cork by the twist, so suggestively let me denote that twisted manifold by upper script tau, then this is diffeomorphic to 3CP2 connexon 20CP2 bar. Okay. So this embedding he constructed by hand. After regluing by the Cork twist, he used complicated Kirby calculus to show that this resulting manifold is actually diffeomorphic to this. So now this philosophy of being able to detect Corks sort of follows from the fact that the Seiberton invariant for once blown up K3 surface is non-zero, while this splits off at 3CP2, so the Seiberton invariant here is 0. So hence, you have detected that Akbulut has proved that this cork is actually in fact a cork. So this is typically the strategy in the literature. So I'm going to take my cork, I'm going to embed in some closed form manifold, and then somehow I'm going to show that after, if I reglue by the cork twist, I'm going to change a four manifold invariant. The proof of Akbulut cork being strong sort of also followed a similar strategy, like being able to embed the Akbulut cork in some four manifold. Okay, so that's about how to detect corks, and now let's discuss what are the candidates. So what do we need? What do we need for a cork? So we need a homology sphere, and then we need a contractible C such that del C is Y, and we need a homology sphere with a diffeomorphism. That's all. This is like the basic requirement, and then you sort of make some effort to show that tau does not extend over C. Okay, so now let's think about where can I get possibly this basic set of things from which I can hope to build a cork. Well, as I said before, like briefly alluded to earlier, that whenever you take surgery on slice knots, they always bound a contractible manifold. So they are good classes of manifolds which can be considered as a basic data from which maybe you'll get a cork. Okay, so recall surgery on slice knots bound contractible manifold. For example, 946 we saw. So maybe we can start there. Okay. So we can start at the knot table and try to list the slice knots one by one, and then try to prove that for each of these slice knots, can I put in a diffeomorphism when I do on a three manifold that's obtained by doing Dane's surgery on that knot, and then I ask, can I prove that these are corks? Okay. They automatically already going to bound a contractible manifold, so that part is solved.
Sorry?
Yes?
Which surgeries?
So because we want integer homology sphere, we mean plus or minus like 1 over n surgery, plus or minus 1 over n. Yeah.
Okay.
Sorry, I should have specified this. Okay, so I mean we can try to execute that strategy. The thing is, the simplest, just not write it. The simplest slice knot in the knot table is the Stevedore knot 6-1. By simplest, I mean comes if we consider the enumeration. This is not first. But the thing is, it was open until very recently, and I'm going to talk about it, that whether if I do, let's say, plus or minus 1 or whatever surgery to it, so this knot is symmetric. So by doing a similar operation that I had here, where I erased the thing, there's an axis coming out, there's some knot symmetry here that will always induce involution on the surgered manifold. This will always have a contractible manifold, but even showing for the simplest slice knot whether this is a cork or not was open, and it was answered very recently. I'm going to talk about it later. To demonstrate the fact that finding corks is not that easy. Like following these sort of strategies of looking at surgeries on slice knots, where you have an obvious contractible bound, it does not always pan out. And the reason behind this is following. Being able to embed a cork in a spore manifold where you know beforehand the Seibertine invariant, and showing that changing by the twist will change the Seibertine invariant is a difficult task. And sometimes you borderline have to get very lucky for a prospective cork to work following this strategy. So I'll just write, something like this is hard. Okay, that's fine. Maybe by looking at very specific slice knots, going through the knot table, it's maybe not the best thing to do. A very obvious class of slice knots come from the following. So I take any knot k, okay, I connect some k with its concordant inverse. So k connects some concordant inverse of k is by definition a slice knot, always, for any knot k. This is the concordance inverse. By concordance inverse, I mean basically you mirror k and you switch the orientation. So if you connect some for these two knots for any knot k, you'll always get slice knots. And maybe you can ask, well, this is a systematic family of slice knots which I can do for any, I can start the process of any knot. For example, this knot k need not be sliced to begin with. I can do this for trefoil, for example. Trefoil connects some, negative trefoil will bound to slice this. And I can ask, maybe this process gives me, following this sort of strategy, maybe this gives me candidates for Corks. Seems like something that one should explore.
That's not trefoil star, right? Minus k is...
Minus k is mirror of trefoil, and you switch the orientation. So you switch the crossings, and you switch the orientation. You start with the orientation of the trefoil, and then you do this. Okay, so knot is fine. So maybe I'll take this knot to start with. I'll have a contractible bound, but this diffeomorphism that I need to care about. So what sort of symmetry I can think of this knot that will induce a symmetry of the Searcher manifold? Let's think about that. So here's an interesting symmetry that you can put on. Not just k connects some mirror k connects some any knot. So here's a Cartman's description of k connects some other knot j, and here is the diffeomorphism, symmetry that I'm going to consider on this knot. So what I'm going to do is that I'm going to consider a torus that follows, that is the regular neighborhood of the knot k. But when it comes near j, it's going to engulf j like this. This torus is typically known as the swallow-follow torus. So here is a symmetry of this connected sum knot. So the way you think of this is that you do a Dane twist, a full Dane twist on this torus that will send the knot back to itself. But because while you're doing the Dane twist, you're sort of dragging the ambient space with you, that could act non-trivially. I mean, it's not clear that why should that be trivial. So let me denote this sort of action by small s. So now you can ask the following question. If I consider, let's say, +1 surgery on k connects some negative k with s and the contractible manifold that I'll get because this is a slice knot, you can ask, is this a Cork? Seems like a natural classes of Corks for which we should at least ponder what should be the answer. And indeed, this was studied by Gompf. So Bob Gompf in 2016 showed that, answered this question by showing that, sometimes indeed this is a Cork. So for which knots k specifically is this? Well, so the knots he considered come from this doubly infinite family. So this doubly infinite family knots, this doubly infinite family is sort of defined as follows. So he showed that for this very specific family of knots, KRS, and RNS could be any positive integer, and they represent like positive twist. So for this specific family of knots, this sort of operation actually gives you a cork. And in fact, he showed something slightly stronger. So what he showed is that if you can consider 1 over T surgery on K connexum minus K, and the power of S could be any natural number, then this is a cork. So it's sort of clear when I explained this that you don't have to stop at like one twist. You can just keep repeating this twist, and this is in some sense an infinite order thing that you could just keep repeating. And what Gompf showed is that for any 1 over n surgery, 1 over p surgery on this knot, you have an integer homology sphere that will bound a contractible manifold, and any power of this twisting thing, it will always give you a cork. Okay, so seeing the peculiarity of this specific family, he posed the following question. What other knots K satisfy this? So for what other knots K can I get a positive answer to this question? Yes?
I'm not sure I understood the definition of S, and wasn't S supposed to be an involution?
Well, S is not necessary. So when I wrote down the definition of like the cork, it was I wrote it as a diffeomorphism. It is an artifact that, for example, the absolute cork was an involution. So it's not necessarily as an involution. And the definition of S is you should think of it as doing a Dane twist, a full, let's say, right-handed Dane twist on this torus sitting inside S3. Okay.
N and P has no relation, right?
Say that again?
P and N.
P and N, sorry, I should have mentioned. So where indeed P and N are any positive integer. Any positive integer. In fact, you can take P to be negative as well. You can mirror things and things like that.
For this twist, not double twist, is there any relation?
For the twist not here or RNS, no. They are also where for example, like if you pick R equal 1 and S equal 1, it will be the figure 8 knot. So the family starts at the figure 8 knot. Okay, so how did Gompf show that these are corks? How did Gompf prove this? Well, his strategy was exactly the same thing that is written in this part of the board. That is, he embedded this cork inside a closed four manifold. In this case, it was some elliptic surface. And then he showed when you just keep redoing by the boundary twist, that corresponds to doing what's called a Fintugel-Stern knot surgery. But those knot surgery was done along knots with varying Alexander polynomial. So there is a formula for computing Seiberg-Witten invariant of four manifolds. This sort of relates the Seiberg-Witten invariant of four manifolds where you do Fintugel-Stern knot surgery with the original four manifold. And those are related by, let's say, a product of the Alexander polynomial of the knot on which you're doing Fintugel-Stern surgery. So in other words, whenever you're doing Fintugel-Stern knot surgery on knots with varying Alexander polynomial, you're guaranteed to get different Seiberg-Witten invariants every time. So that is how Gompf was able to show that for any power of S, these are Corks. He had an embedding inside some elliptic manifold, and then he shows that the Seiberg-Witten invariant is going to change every time. So the strategy, keeping true to the strategy. Okay. So at this point, let me sort of remind you. So the thing that sort of wrote, like few boards earlier here, was that the question that sort of interests us, or at least, one motivation the way I've been presenting to you is, for studying Corks is that I want to know, I want to think about exotic four manifolds. and I want to study quarks for this. But you see, the strategy for detecting quarks is actually factoring through finding four-manifold invariants. Okay? So my main motivation was to study exotic four-manifolds, and I said, well, quarks will be a tool for me to find these examples. But if I'm finding quarks using exotic four-manifolds itself, then the flow is sort of different. I want to flow this way. I want to find quarks and then go here, but this is flowing somewhat this way. Okay? So typically, that is why it has been hard to find examples of new quarks in the literature. I want to have, let's say, a four-manifold invariant free proof of showing something is a quark. By the way, I should mention that it is known there are some negative results for this question. So right after this paper came out, Ray and Ruberman showed that you do not get a quark for any k equal torus knot. So if you start with the knot k being a torus knot, then these sort of twisting things, this Dane twist type of thing, will always extend to the boundary contractible manifold smoothly. So this is in some sense a negative result. It is not obvious. There's something interesting going on. So for example, as I said, the family starts at figure 8. So for figure 8 knot, this sort of operation will give you a quark, whereas for, let's say, a trefoil knot, this operation will not give you a quark. It sounds slightly mysterious the way I've been presenting to you, and my claim is the answer actually lies in Heegaard Floer homology, at least to clarify this part of the mystery. All right. Yes, this is for. So using symmetry to detect symmetry in Heegaard Floer homology. Okay. So now, at this point, my motivation is can I find a four-manifold invariant free way of detecting quarks? So that might be useful. So the idea is that we are going to study the action of the diffeomorphism that a quark already has on the Heegaard Floer homology of the boundary. So recall, so there is a Heegaard data. We are not going to talk about what do I mean by this. There's an underlying data you need to specify for a three-manifold. Why? Then the action of a diffeomorphism tau noi on the Heegaard Floer chain complex is defined as follows. So there's some underlying data I need to fix. Let's not talk about it, but assuming that I fix the underlying data, this is the Heegaard Floer chain complex. Okay. So what do I do is that I take this diffeomorphism that's on Y. So what I'm trying to do now is that given a diffeomorphism on three-manifold, I want to define the action of the diffeomorphism on the Floer chain complex. That is what I'm trying to do. So I start with the Heegaard data. I take the push forward of the Heegaard data by the diffeomorphism. Then this pushed forward data still represents the same three-manifold because I've just taken a diffeomorphism. So there is a canonical choice of chain homotopy equivalence that's going to take this chain complex and end in the original chain complex that I had in the beginning. So this is a chain homotopy equivalence. This was originally defined by Zuhas, Thurston, and Zemke. So the action of tau on the Floer chain complex is defined as a composition of these two maps. It is an automorphism. That's really the point. So coming back to the original thing. So in 21, Irving, Matt Hedden, and myself defined two invariants. Let me just talk about one. There are invariants, let me call it. So the invariants sort of take shape of a pair. So I have a chain complex, a Heegaard Floer chain complex, and I have this diffeomorphism, the action of the diffeomorphism that we just defined here. There are invariants which considers the pair Cf of y with tau modulo certain equivalence relation such that if this pair, so when I say modulo equivalence relation, I'm going to put the square bracket here. If this is non-zero, not explained correctly, what do you mean by this? Also not explained what is the equivalence relation, but anyway. If this is non-zero, then y tau is a strong chord. So there's a way to package the action of the diffeomorphism on the boundary with the Floer chain complex group and quotient this thing out by certain equivalence relation so that the resulting thing, when you know that that's non-trivial, that will tell you tau is not going to extend over any homology ball that y may bound. In particular, so just to give you a quick summary of how this typically works. So example. So consider the Abhishek chord. So it turns out that there exists a cobordism from +1 surgery on 946 to the Gompf homology sphere sigma 237 equipped with some other diffeomorphism. Okay, so let me take a step back first. So what do I need to do to compute this invariant? I actually need to compute the action of tau on the Floer chain complex defined this way. Okay, that is the primary thing I have to do. But this is a very hard task. So the reason behind this is it's absolutely unclear how does this chain homotopy equivalence gonna send my generators, act on my generators. It's like this is an abstractly defined map and we don't really have a hand on how it's gonna act. So in general, if I give you a diffeomorphism acting on a three manifold, it's a very hard task for you to actually compute the action of the diffeomorphism. So the idea is that, if I want to show that, apply this to show that the Abhishek chord is strong, well, I'll probably not be able to compute the action of tau on the Floer chain complex here, but what I'll do is that I'll estimate the action by computing the action on some simpler three manifold, and this is the simpler three manifold. Gompf homology sphere sigma 237 is Floer homology is quite simple. We know how to compute the action of the diffeomorphism of the Gompf. So we construct the way we estimate. The estimation part comes from this geometric data. So I have this diffeomorphism acting on +1 surgery in 946. I consider an equivariant negative definite cobordism from +1 surgery in 946 to sigma 237. By equivariant, I mean this cobordism is equipped with a diffeomorphism that restricts to tau on this side and some other diffeomorphism on this side. So this geometric data sort of translates to the following. So at +1 surgery and 946 with tau. And now after some manipulation, you'll be able to show that this is strictly less than the floor chain complex of sigma 237 with this tau tilde. Okay, so I'll put this in quotation because I haven't really explained what this is. This is some relation in this in this these line segment groups. So there's some relation in this group, but this you can show is actually strictly less than 0. So in particular, this shows that this invariant is non-zero. So this is typically how a proof of something is a Cork goes without four-manifold invariant using this strategy. So this is a proof, for example, a very hand-wavy proof of Akbarut Cork is a strong Cork without using any four-manifold invariant. All right, so at this point, if we are following, it should be sort of clear what could be a potential strategy to answer Gomph's question. The potential strategy would be, can I compute this Dane twist action on the floor chain complex? So let me consider +1 just to simplify things. Because I want to apply this thing that I just erased. So there are some invariants that do not really care about the four-manifold invariant, and maybe the four-manifold invariant strategy was quite hard. So let's see if we can make progress here. So the question is, can I compute this action? And maybe they'll be able to. And the thing is, in this situation, it just so happens that this diffeomorphism is simple enough that you can actually completely compute it. So this is typically what's known in the literature as the shortcut map, or sort of STAME, so the shortcut map. And where this acts is that, so let me explain what a shortcut map is. Shortcut map is, suppose I have a knot. So I can fix a point in the knot, and I can take the point and drag it all the way across the knot back to itself. During this process, it's going to drag the ambient space with me. So the trace of the isotopy defines me a map here. So that, let me call that map shortcut map. So what this S is doing is that it's sort of doing a similar thing. So you can think of this, shrinking this negative k into a very small ball, and you just rotate that ball all the way around. During this process, you're not doing anything to the negative k factor, but on the k factor, it's sort of applying the shortcut map. So this map S here is precisely under the Kunait formula. This is the shortcut map on k tensor identity, because you're not really doing anything to the negative k factor. So and this map is computed. So this is computed by shortcutting 11, and in more generality, by Zemke, I think in 60. All right, so we know the action of the map. We know, so computing the floor chain complex is also not that hard. There are some certain surgery formulas that are in my hand that I can use this to compute. So I can ask, what happens to this invariant? So sadly, it turns out that, so unfortunately, this invariant that I just wrote down actually ends up being trivial. So there is no information to be had from these sort of invariants. So what is the point? Why am I telling you all of this? So now we're going to compute an explicit example. So we're going to consider an example, and we'll see how do we overcome. Unfortunately, the thing that I've been sort of preaching to you, that there are ways to get Corks without using four-manifold invariant fails. And typically, expectedly, using the four-manifold track would be also hard, because otherwise Gompf would have answered this already. So what is the way out? So recall that this family, this bi-infinite family KR, started at the figure 8 knot. So we'll consider the figure 8 knot example. So I'm first going to tell you an idea, sort of a brief idea of how do we how do we show that this is, let's say, a strong Cork, and then I'll explain what exactly our results are. So firstly, the idea is, again, I'm going to estimate this manifold by some other manifold, and in this case, the other manifold is going to be, the estimated manifold is going to be some large coefficient surgery. So I have +1 surgery on 946. Previously I had sigma 227 on this side, and now I'm going to have some large odd number here. Doesn't really matter. This is just a large coefficient. Now they will always be equipped with the same type of diffeomorphism. Sorry, I don't know where I wrote 946. 4-1 is a figure 8 knot. 4-1 and some minus 4. Okay. So there'll be some cobordism between them. There's going to be again a negative definite covariant cobordism from this manifold to this large manifold, and this will play the part of this estimation thing. And now let me write down the Floer homology of this large surgery complex. So the Floer homology. So let's say so the Floer homology looks like this. So the version of Heegaard Floer homology we're considering is an FU module. Okay, so there is an action of U. So it's going to look like this. So there will be a U non-torsion tower that I'm sort of depicting like this. So there is a top generator, and they'll have U multiples going down. And there are 4 torsion elements. So let me represent by X the top of the FU tower, and the torsion elements as A, B, C, D. This will be the Floer homology of the estimated thing. My aim here is to somehow, compute the action of S in this situation. So it turns out that the action of S is going to go like this. So it's going to preserve X, it's going to preserve A, it's going to preserve B. It's going to send C to itself and to D, and it's going to preserve D. So this relation here is read as S of C is C plus D. Okay. So we will come back to this example momentarily. So let me now give you an obstruction. So suppose that tau on Y extends over a homology ball W, then we must have a homology class X in Floer homology of Y such that the following is true, that X is U non-torsion, meaning U multiples of X, and never die. The action of tau preserves the homology class of X, and then the mass log gradient of X is 0. So this is after certain universal grading shift. So this is to say that X lies in the very top mass log gradient. We can also sketch a very quick proof of this obstruction. It's not that hard. So the idea is, suppose, on the contrary, you see the hypothesis is not, let's say it's not a Cork. So suppose Y has a tau that extends over some W. So what you do is that you puncture W, so you get an S3 here, and you consider this cobordism. You get a cobordism map from CF of S3 to CF of Y. And this cobordism map, because this diffeomorphism extends, is going to intertwine with the action of tau. And this element X here is precisely going to be the image of the generator of CF of S3, which is just an FU tower. There are no torsion here. So if you look at the image of 1, the top dimensional generator, that will define you this X3, this element X. by definition, this element x will be preserved because this difference is extended. All right, so we can try to apply this sort of obstruction here, and unfortunately, you see here, you see x is a U non-torsion tower generator. It lies in a top grading, so by mass love grading 0, this is the mass love grading 0. So there's a Z grading. Spheres, and x lies in a top grading. Moreover, you see the action of the diffeomorphism preserves x. Okay? So this obstruction, sort of similar to this situation, is not that helpful. But there is a certain modification of this obstruction. Let me call it 2.5, where instead of just considering the action of tau, you can also consider what's called the spin C conjugation action. So there's an iota action here. This is the spin C conjugation. So you can show by, again, similar strategy that because this is a homology ball, and hence W is a spin manifold, you have a spin cobordism between S3 and W, spin homology cobordism, that in this situation, the action of spin C conjugation on the floor chain complex also must preserve the class that is preserved by tau, because this class is defined by the same element here. Now, you can try to again compute the action of spin C conjugation on this surgeon manifold. So let's write down the computation. So this was computed. So this is again the Floer homology of some large surgery on 4-1 connects on 4-1. But now instead of talking about the diffeomorphism action, now I'm going to write the iota action, the spin C conjugation action. So this was computed by Hendricks, or rather follows from the work of Hendricks and Mallick. So this action is defined as follows. So x maps to x, it maps to A, it maps to B, and it maps to D. Okay. A maps to itself and to D, B maps to itself, to D, C maps to itself, to B, to A, and D maps to itself. This is slightly more complicated behavior than the previous thing we saw. But interestingly, you see the x, which is sort of supposed to be fixed by tau, is not fixed by iota. So you see iota of x is x, then I have an arrow to A, an arrow to B, an arrow to D. So, this obstruction does not apply to x. And maybe you're like, well, maybe x by itself need not be true. Maybe change some basis elements, and maybe you can find such an x where this obstruction will apply. The thing is that there will be no such x. You can sit down and try to find a common x that is fixed by both iota and tau that will satisfy the other condition, and you will not find it. What does this show? This shows that this tau for +1 surgery on 4-1 connects on negative 4-1 never extend over a homology ball. So this implies. So this implies +1 surgery on 4-1 connects on negative 4-1 is with S is a strong torque. Now let me quickly mention the more general theorem we prove. So, okay, fine. This is like a four-manifold invariant free proof of something that was already known before. But like, what can we say? So there is an invariant. There is a not concordance invariant called connected complex. So let me denote this as C connected of a given knot K. This is defined by Hendricks, Hom, and Lidman. So what we show is that if the short card map is not homotopic to identity on this connected complex K, then +1 surgery on K and some negative K with the action of S is a strong call. Okay. We don't, I'm not going to go into much details here, but just to give you some examples, or rather like one obvious way of figuring out what examples that we can get using these sort of things, that when should we expect this action to be non-trivial. We call the shortcut map was take a point and not move it all the way around. So if you consider the figure 8 knot, the chain complex for the figure 8 knot looks as follows. There are like 5 generators. And so there's 1 generator here, there's 4 generators that come along a cyclic box. So there's certain knots that are called thin knots. So for thin knots, if you see these sort of boxes in the main diagonal, and if they appear in odd number, then they are sort of guaranteed to satisfy this condition. So in particular, figure 8 knot this is the what's called the knot for chain complex. So the figure 8 knot has only 1 box, so it satisfies this condition, and hence sort of knowing already that this is going to be this computation wasn't really required. We could have shown this on this obstruction. If you consider the trefoil knot, sorry, I'm going to stop. Really, you see, this is a chain complex for the trefoil knot, and you see there is no box in the main diagonal. In particular, there is like 0 box. Okay, it's the even number of box. So actually, indeed, it turns out, as shown by Ray and Ruhrmann, for the trefoil, this will not be true. The tau will always actually extend. Here's another example. So instead of considering just the trefoil knot, you could have considered, let's say, the trefoil connects on the trefoil. And in that case, the knot for chain complex looks like this. And in the main diagonal, there is again only 1 box here. So it's odd number of box. So indeed, this theorem tells you that even though for any torus knot, this, this action will always extend, if you just consider the connect sum of 2 simplest torus knot, this action will not extend. So if you consider K to be T23 connect sum T23, then this will turn out to be. So there are many such examples that sort of satisfy this hypothesis. Most of them is not covered by Gompf. All right, I'll stop here. Thank you.
Are there any questions? I have a question. So the last examples are related somehow to V0 upper being not equal to V0 or V0 lower being different than V0?
Well, the thing is, the action here, you mean for iota? For
iota, yes.
Yeah, for iota, there is some relation, yes. Because you want, you at least want this S to be, the shortcut map to be non-trivial. So you should expect, just having, at least for thin knots, right, having odd number of boxes is important, which in turn, some situations does tell you confirmation.
Are there any questions? If not, let's thank Abhishek again.